instead of df minus h, which I just showed you. This will show how many inodes I've currently used and how many inodes I have free. Notice that this is different than, sorry, let's compare this output. So df minus h, what does that show me? Actual memory I have left. So if you look on my hard drive, I've used up 16%. But why is this, df minus I, telling me I've used up 5%? What's the difference?
5% of the inodes.
I've used up 5% of my inodes. So here's a question I'd like to ask on a test. Is it possible for me to run out of space? I don't know how I say it. How do I say it? Is it possible for me to use up all my inodes before I run out of space on my disk? Yes. Is it possible for me to run out of space on my disk before I've used up all my inodes?
Yes.
Yes. Either one. So that is possible. So this shows us the amount of the number of inodes, the inodes free, inodes used, and inodes. Okay. LS doesn't access inode metadata, but LS minus L does. So if I just do LS, that just gives me the names of files in my directory. But LS minus L, this is all the rest of this stuff, is all inode stored in the inode somewhere. And if I do an LS minus LI, this even gives me the inode number that refers to readme.txt. Okay. Same thing, stat command. So if I do stat readme.txt, that also accesses some of the inode information. We know, we just said the inode does not store the file name, but it does. The inode information does store some of the permission stuff and some other information about the file.
How does it know which file it is if it doesn't store the file name?
Ah, okay. So all our, good point, all our directory tree is a list of file names, and those file names refer to an inode. So that's how they map the two together. So one example, and we've done this before, but let's do it again because I think symbolic links and hard links are a good way to display the difference or how inodes work, I guess. So if I create ln minus s, I'm going to create a symbolic link to my readme.txt symbol. I'll just call it symlink. So here I am, ls minus l. We know that a symbolic link, we've done symbolic links a couple weeks ago, we've done an IT-3100, should be familiar with it now. But all it does is it points to this name readme.txt. What if I delete readme.txt? Points to nothing. Okay, well let's do ls minus li for a second. Oops, if I can type. So let's keep track of these. So symlink points to readme, and readme is at this inode number, 5824. Okay. And so we've just said, if I delete readme.txt, this is just pointing to a file name. It's not pointing to an inode. Anything that has that file name, symlink will point to. So I'm going to remove readme, and then obviously it's broken, changes color. If I cat out symlink, it doesn't work. I'm going to go ahead and touch readme.txt again, and let's look at the inode. Oh, it was actually reassigned the same inode that it had a second ago. So I don't like that, so I'm going to remove that. Now that file has it. Now I'll touch my readme file. Oops, I'll touch my readme file again. Touch. So now readme has a new inode number, but it doesn't matter. Oh, I didn't type readme.txt. Oh, I didn't type. So my symlink is okay. All right, so we've just established that the symlink has nothing to do with the inode number. It just points to the name. Whatever the name is, that's what we're going to point to. Now, if I do a hard link, so how do we do a hard link? Just no minus s. So target is going to be readme.txt, and my hard link, I'll just call it hard link. Note that hard link refers to number 831, and readme.txt is 831. What happens if I delete readme.txt, can I still get to the data?
No. Yes?
Yes.
Because
With,
the hard link,
by referring to the hard link, yes.
because a hard link does both of the, like, it synchronizes the changes, but they're stored in both files, right?
Well, it's only one file, there's only one file that exists here. Just I have two directory mappings that go to inode 5831. And so if I delete readme, I've deleted that mapping to, oh, I'm sorry, readme.txt. Let's just remove that one, so that's weird. If I remove readme.txt that maps to 5831, can I still get to the data? Yeah, because hard link maps to the same inode. So that's how that works. Hard links map to the inode, symlinks just map to the name. Okay, let's look at some other, so files can have multiple names, which with a hard link, right, I can create another one. I could say, all right, I want this, oh, and I could do hard link, foo-foo. And so this one also points to 783 or 831, ending in 831. So now I have three files that point to the same inode. If I delete one, that's okay, I can still get to it through the other one. But it's not creating a copy of the file, it's not a copy. It is the exact, we go to the exact same set of blocks on our partition to access the data. Questions on that? An inode may have no links. Hard to find if it doesn't, yeah.
So if you were to delete the README, then you're saying that you can still get to that data through the hard link. So when you delete a file name, it doesn't remove the data in the inode?
Correct. Correct.
Do you overwrite the inode?
We can reuse the inode, as we just saw when I deleted readme.txt the first time. So basically, let's remove it. Let's remove foo-foo. And we know that this, so that was pointing to 831. These two still point to 831. Blah, blah, blah. And so let's cat out our hard link, and let's cat out our readme. Those both are pointing to the same set of blocks, so that's why I'm getting the same data. If I remove hard link, can I still cat out readme? Sure, because it's still pointing to those blocks. But now, if I remove readme.txt, do I have anything now that points to inode 831?
No.
I don't. Now that the data is still there. It's still on disk at this point. I just have no way of getting to it. There are some advanced file recovery tools that will go and they can go back through your disk and find that. We're not doing that in this class. But for all intents and purposes, the operating system now says, oh, well, 831, that's not being used. I can reallocate that number wherever I want and then reallocate those blocks. So, in a, what do they call it? Computer forensics investigation or whatever, they want to grab this disk image as soon as they can so that those blocks aren't overwritten. But the blocks are still there. Nothing has overwritten that particular data, I would assume, yet. Yeah.
So is there a way to delete both the file name and all the data within the inode?
So you could delete the file name with the rm command. To wipe the data in the inode, you would have to, yes, there's some different commands you can use to go and do that. It's getting beyond the scope of this class, and I can't remember that off the top of my head. So, but there is ways to go and do that. Okay, so here's some other things, some gotchas. Like I said, which we just asked, an inode may have no links. Meaning, an inode still exists, it's there on disk, but I have no way to get to it. In my file systems class, we go and we did what I just did. We delete all file names that point to an inode, and then we use some command that goes back, and we can go back and, it's really weird, but we can get back to the inode at some point, and or wipe it. Here's the other two rules. A file's inode number stays the same when moved to another directory on the same device. That's why, even if my file is like 5 gigs in size, if I'm doing an MV command and I'm just moving it from one location on my file system tree